So we are going to learn about different representations of the traditional Lewis dot structures that you've learned before, and the most common representations for organic chemistry specifically. So there's four types we're going to talk about in this video. The first is Kikuli, which is a displayed structure and very similar to the Lewis dot structures that you already know. Then we'll get into structural, condensed, and then skeletal or line bond structures are going to be the real key for the rest of your year in organic chemistry. So Kikuli structures, they're named for this German guy who basically helped found chemical structure theory in general. And so he was one of the first to have dot structures named after him, like Lewis, right? So these show all of your atoms, all of your bonds between the atoms. They're very, very similar to the Lewis dot structures that you've drawn in the past, except that lone pairs are often not shown. So you assume that when someone has drawn a Kikuli structure, that they understand the octet rule and that all of those elements are obeying the octet rule, except for hydrogen, which is the duet, so no lone pairs there. But you make the assumption that those lone pairs that would complete an element's octet are present on that molecule. So here's some examples of some Kikuli structures. This is CH3Br, and again, it looks really similar to a Lewis dot structure, but we're just missing the lone pairs around the bromine. Again, same with here, this is methanol. It looks very similar, we're just missing the lone pairs around the oxygen, and those are again assumed to exist. Here are some other examples, all looking pretty similar. So if you're taking notes, you're going to want to write these structures down because we're going to use these same 5 structures over and over again to learn how to do the other 3 types of structures we will be talking about. So the second type of structures are called structural structures, which is a little redundant. These are really similar to your Kikuli structures, except that we start to eliminate some of the bonds that we're drawing. So we start to eliminate bonds to hydrogen if they're coming from a carbon, nitrogen, or oxygen. So the numbers of hydrogens bonded to those elements are instead written as a group with a subscript, like H2, H3, however many are bonded, or if it's one, there's no subscript at all. And the other bonds between any other elements that are not hydrogen are still shown. And again, lone pairs are often not really shown here either. So let's look at our 5 examples and how I would convert these into structural structures. So I'm going to leave this carbon and Br bond because that doesn't involve a hydrogen. But then instead of drawing all of these separate bonds from carbon to hydrogen, I'm just going to write H and then 3. And it's assumed that these 3 hydrogens are bonded to the carbon as they are in the structure here. Let's look at methanol down below. Again, that C and O bond is going to be preserved because it's not to a hydrogen. But then similarly to our example up here, I'm going to do an H3 next to this carbon to show that there's 3 hydrogens bonded to it. And then I'm just going to put one H written right next to the oxygen. I don't need a subscript of 1. We're basically just eliminating drawing that bond in between that oxygen and hydrogen. Let's move on to the next one. So again, here I'm going to preserve this double bond between these carbons as well as preserve the bond to this nitrogen. This carbon on the far left has 2 hydrogens attached, so I'm going to put H2. Now what gets tricky is, for example, this carbon here is in the middle, so it's hard to know where to put that hydrogen without drawing the bond because we've already got bonds on either side. So you're just going to write that H either above or below. It doesn't matter which side. And then the nitrogen has 2 hydrogens attached, so I would go H2 here. All right, let's try out the rest. So again, I'm going to draw this triple bond between this carbon, and then all the rest of the carbon bonds I'm going to draw. This carbon-oxygen bond gets preserved. All right, and now I need to fill in my hydrogen. So I've got 1 hydrogen attached to this carbon on the end here. Okay, no hydrogens attached to this carbon, so I don't need to add anything there. On this carbon, 1 away from that triple bond, I've got two hydrogens. And again, I can write them on the top or the bottom, so I'll write it on the top this time as an example. All right. Next one, C, maybe I'll just do this on the bottom to show you that you have flexibility. The carbon with the double bonded oxygen has no hydrogens, and then this one on the end is CH3. All right, last one here. So again, I'm going to preserve the carbon-nitrogen bond, these carbon-carbon bonds, and this oxygen, and then fill in my hydrogen. So this would be a CH3, this would be NH, this would be CH, this would be CH3, and this would be OH. So that's our example of our structural structures. Now, sometimes when organic chemists type out structures like this, we get lazy, and so you'll often see them instead maybe written like this. And so it's still representing the same thing. It's just that chemists are getting lazy because we can't really type the hydrogens above and below the carbons. So just make sure you know that these carbons are actually the ones bonded to each other and the hydrogens are bonded to the carbon. It's best to draw it like this so that you can show the carbon-carbon bonds. But again, typing this gets complicated, so sometimes you'll see it like this. If you're asked to draw a skeletal structure, or not a structural structure, you should draw it like this, but sometimes in typing you'll see it this way. So let's move on to condensed structures. Basically, the big summary of this video is chemists just keep getting lazier and lazier with every structure that we learn. All right, so condensed structures omit essentially all of the covalent bonds. And so the bonds are all assumed that they are filled. Everyone follows the octet rule, unless there's a formal charge, which we'll get to soon, and that would have to be indicated in the structure. But any atoms that are bonded to carbons are just listed with subscripts, much like the hydrogens that we did in our previous structure examples, except this time it can be any element. And substituents, which is a name for chemical groups that are hanging off of the main sort of chain of our structure, I'll show you what that looks like in a second, are listed with parentheses. And so I'm going to do a bunch of examples so that it's a little less confusing. So these are the structural structures that we just talked about on the last page. And now we're going to take these structural structures and we're going to convert them into condensed structures. Generally, when I write condensed structures, you're going to write the carbon first and what's bonded to after it. So unlike in the structural structure where I write the hydrogens first because I want to show that carbon-bromine bond, when I write my condensed structure, I'm going to write carbon first, then my three hydrogens, then my Br. And just like when you got a formula to draw a Lewis dot structure before, it's assumed that you understand that this carbon is the central atom with everything else bonded to it. Similarly with methanol below, I'm going to write the carbon first. All right, so I'm going to do CH3OH. It would not be a proper condensed structure here to write this, even though that is the formula of the compound. That's not showing you how it's bonded, right? There aren't 4 hydrogens and an oxygen bonded to that carbon, so you do have to write it out as it is bonded in the structure. All right, moving up here, this would be CH2, then CH, then NH2. You're always just going to work left to right if it's drawn for you. All right, down here, CH, then just C, then CH2, CH2, CO, CH3. So sometimes condensed structures are not actually the most practical way to write a structure, and this might be an example where that's true. It's sort of hard to figure out the bonding in this structure when it's written this way, and so condensed structures would probably not be a natural way that we would write out this particular structure. All right, so this next example has an example of a substituent that I mentioned before. And again, substituents are groups that are coming off the main chain. So if we treat this right here as our main chain of atoms, then our substituent is this CH3 that's hanging off the end, right? It's bonded to the carbon instead of continuing making this molecule a straight line. And so like the bullet points above said, we're going to write that in parentheses. So I'm going to start normally, CH3, then NH, okay? Then I have CH, and I have this CH3 hanging off of this carbon right here. So far I've drawn or written this here, but I need to indicate that that CH3 is hanging off of this carbon instead of just next in the line. And so the way that I do that is put this in parentheses and put CH3, and then I move on and finish the molecule, which would be OH. So what that's telling the reader is that this CH3 is attached to this carbon, this hydrogen is attached to this carbon, and you have to jump over and see that this OH continues the main chain of the molecule, so it is also bonded to this carbon. So those are your condensed structures, and next we're going to move into the extra super lazy structure way. So first I'm going to just talk about some theory of skeletal or line bond structures. You'll see them called both things. These are some example of some skeletal or line bond structures. So these are definitely the biggest departure from the Lewis dot structures that you've drawn before. And so we're going to slow down and take some time just to give you the basics before we get into our practice. Okay, so carbon-carbon bonds are shown as lines. You never draw carbons or hydrogens in these line bond structures. Everywhere that there is a vertex or an endpoint would represent a new carbon on your chain or in your molecule. So for example, if I look at some of the examples down here, let's look at this lower one because it's the most simple with only single bonds. Here's a carbon, here's a carbon, here's a carbon, here's a carbon, right? There are all those points where you can sort of see the breaks in the line that you're drawing. And again, here, 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 here for the one with the double bond. The one with the triple bond is the hardest because the triple bond is drawn in a straight line in order to represent the 180-degree bond angle accurately. So these three are carbons, and then where the triple bond starts is a carbon, where it ends is a carbon, and then where that continues is a carbon. And again, this is sort of the exception to the rule when it comes to line bond, that we do this 180 degrees here because it is a triple bond. Everything else you're going to draw in this zigzag pattern to represent the bond angle and to just make it easier to identify where the carbons are. All right. So, like I just said, carbons are drawn in the zigzag format, except for the triple bonds where we show a straight line with that 180-degree bond angle. And the number of hydrogens is assumed to fill your octet unless there's a formal charge, right? Which again would have to be indicated. And again, you're not going to draw any hydrogens unless it's bonded to an oxygen or nitrogen. That's the only time you will show hydrogens in your structure. But any carbon-hydrogen bonds are just getting eliminated. They're being drawn as these zigzags, and they're assumed to fill the octet rule as needed. But if you do have a hydrogen on a nitrogen or oxygen, you will still draw that. So let's look at our examples. I left the Kekulé structures up here this time because they're the easiest to interpret sort of where you're going with these line bond structures. So I'm going to walk through these examples and then I'll give some sort of tips and tricks on the next page. So the easiest thing first to do, or the most important thing to do first, is just identify how many carbons, and here I just have one. So again, a carbon is represented by an endpoint or a vertex in the line. Okay, so since this is an endpoint, this is a carbon. And this would also be a carbon if I just left it like this, but instead I know that there's a Br there. All right, so that's it for this structure. What it's saying to you, what's implied here, is this endpoint is my carbon, and then all the hydrogens attached are implied to complete carbon's octet. Right, but really all you would draw is that straight line with the Br on the end. Okay, now this right here is not a carbon because we're showing that this carbon is bonded to bromine. So this has one carbon and then that bromine bond. Let's look at the next one. Again, there's only one carbon in this structure. So I'm going to draw that straight line. Okay, my hydrogens are implied, but on this end I have an oxygen. And then there is a hydrogen bonded to that oxygen, which will be the only hydrogen I'll show. And I'll do that in the more structural structure format without the bond between. So those are the one carbon examples. They look sort of weird because they're just straight line. It gets more complex as we get into it a little bit more. All right, so let's go to the middle top. Here I have two carbons and they've got a double bond between them and then a nitrogen. So it doesn't matter if I start sort of going up, or if I start going down, it doesn't matter. I'm going to draw it one way, and then I'll draw you the other way that would also be correct. So I'm going to draw this line here, and then bonded to that second carbon is the nitrogen, right? Between these two carbons that I've just drawn, there's a double bond. So I need to add another line to represent a double bond. And then because my nitrogen has hydrogens attached, I'm going to show those, and it's going to look like this. So that's your structure, right? Your two implied carbons are right here. And then it's saying that this carbon is bonded to the nitrogen, and that's the end of the molecule. I drew my double bond just by adding a second line right here to show that there's two bonds between those carbons. So again, the hydrogens are implied to fill the octet rule. Now there will be less hydrogens because of that double bond, right? So something to keep in mind. If I wanted to draw it by sort of zigzagging down first, it would look like this. Add my double bond on the outside, and that represents the same thing. All right, let's move to the next one. Again, I'm sort of going to identify where my zigzags are going to happen. Now, in the middle of my zigzag, I have a nitrogen. I can still use that as a sort of vertex point because there's a carbon that comes afterwards. All right, and then the end of my line will be this oxygen and hydrogen. So again, doesn't matter if I start up or down. So I'm going to start by going up. This end point right here is assumed to be a carbon, and attached to that carbon is this nitrogen that has a hydrogen attached. Okay, so I just zigged up, so now I'm going to zag back down for my carbon on the other side of that nitrogen, and then back up where I'll put my OH. I also have to make sure that I add this CH3 group right here, which I will do by putting another line here. So I've created another endpoint here, which implies that there's a carbon here and this carbon is attached to it. So that would be the structure. If I went the opposite way first, which is equally as valid, it would look like this. All right, last example has that triple bond in there. So I might actually start working from the right first and draw my zigzags from the right so that I can end with the triple bond. So here are my carbons, 1, 2, 3, 4 carbons, and then 2 more involved in the triple bond. Right, so again, it doesn't matter which side I start from really, or up versus down. So I'm going to go like this. So this represents this carbon here, this represents this carbon here, which means I then need to draw that double bond to oxygen. Okay, then I'm going to move down, that represents this carbon, then up, that represents this carbon, one more, which represents this carbon, and then remember triple bonds are drawn by extending the straight line. So it would look like this so that it reflects the 180-degree bond angle. And that's this one here is represented by the terminal endpoint here. All right, if I wanted to do that by starting the other way, it would look like this. Again, there's no one way that's more correct. Typically, I'll draw it so that those double bonded oxygens are facing upward, but that works just as well too. So those are some examples of a variety of type of line bond structures that you could use. And so let's go over just some general tips and hints, okay? Chains of carbons are always drawn in a zigzag format. The only exception is that triple bond. It doesn't matter if you start by zigging up or zagging down, none of that matters, okay? The number of carbons is not the number of lines that you draw, but it's the number of endpoints or vertices that you have. Okay, now that's critical. Let's look at this example up here, right? You are not going to draw 1, 2, 3, 4, 5 lines. If I did draw 1, 2, 3, 4, 5 lines, I'm actually implying 1, 2, 3, 4, 5, 6 carbons, right? One too many. So I would just need to draw these 4 lines so that I have 1, 2, 3, 4, 5 carbons there. And if I wanted to start by facing upward, which is totally fine, it would look like that. All right. Carbons always are going to have a total of 4 bonds, pretty much always unless it's charged, which again you would need to indicate. So if you needed to determine the number of hydrogens bonded to any carbon, you would do 4 minus the number of bonds shown to that carbon. So for example, let's look up here. There's a carbon here. If I wanted to figure out how many hydrogens were bonded to this carbon, I would do 4 minus the number of bonds shown to this carbon, which is 1, 2. So 4 minus 2 means that there are 2 hydrogens bonded to this carbon that are implied. So this is definitely a new and unique way of drawing structures, but it's really important to understand because it's basically the way that we'll rely on most heavily throughout the year. So let's look at some ways that you know how to draw or represent structures in general, right? In your previous chemistry classes, you learned about empirical and molecular formula, which is the reduced and the actual formula of a structure. Today we learned about condensed formula, which starts to show how things are bonded instead of just which things are present. Then we also learned about the displayed formula, which is most similar to our old Lewis dot structures that we used to draw, except that we eliminate a lot of lone pairs. The structural formula, where we start to condense down those hydrogen bonds, and then the skeletal formula, where we use the zigzagging of lines to represent the carbons and implied hydrogens bonded to those carbons. So we'll do one more big summarizing practice before we go. So let's look at the structural structure first. Remember, the structural structure just eliminates the bonds between hydrogen and anything hydrogen is bonded to. So I'm going to start by just maintaining the bonds between carbons and representing those. So there we go, that should represent all of our carbons. Then attached to this terminal carbon out here, I've got 3 hydrogens. Attached to this first one on the double bond, I've got 1 here as well, and then 2 on these 2, and it doesn't matter where you put them, right, above or below, and then 3 on the external one. So that would be your structural structure. Okay, your condensed structure is going to just start to write these out. You're going to write a lot of ch when you do this. Okay, so CH3 first, then CH, CH again, CH2, CH2, CH3. And because all of these carbons are attached in a straight line, I didn't need to use any parentheses here. All right, and then lastly, our skeletal structure. So again, I'm going to figure out how many carbons are there. 1, 2, 3, 4, 5, 6. So I'm going to draw lines, points, vertices that would represent 6 carbons. So here's 1, 2, then I go 3, 4, 5, 6. And between the second and third carbon, I've got a double bond. So I'm going to draw that here. All right, if I wanted to start by zigging and zagging up instead of down, it would look like this, and my double bond would be here. All right, so we'll get a lot of practice in, but that's your general overview of the different types of structures we'll work with. Particularly, most important, line bond / skeletal. Those are going to be your best friend this year.